Yeah. Okay. So let me quickly summarize what we discussed in the previous lecture. So in the previous lecture, the most important discussion was that there are three important components. If you look at it in a very abstract way, so there is this memory, then there is this data path, and then there is this processor or the core. So this red dashed line is basically your core, where you have this ALU and control unit, and then you have this memory. And we just discussed that the memory is really slow actually. So the main performance bottleneck is the the memory access is slow. So the memory access is the main limitation actually. So this is the typical von Neumann architecture. So that is stored program computer, and nothing more has changed. I mean, for almost several decades. Now, this limitation of this memory is typically known as the von Neumann bottleneck. A couple of other things which you discussed was that when you talk about the performance, performance means the total runtime of a code. So the total execution time of a code, that primarily depends on two important times actually. Primarily, there can be a third thing which will come later. So it is the instruction execution, that is how much time it took to compute. So for which these ALUs are primarily responsible. So for the computation part, and the second is the data movement, like how much time it really took for the data to go from the memory to the control unit or to the ALU. Okay, so these are the two important things which finally determines your runtime. Now, if you simply look into this code, let's say you are executing this code on a computer. So what we are doing is like we are just adding two vectors B and C and putting the result in A, and this is put inside a loop which is running from 1 to n. Now, a programmer will basically look into this code in this fashion. So the programmer, he or she, will look into like how many flops I am doing. So because it is n here, so for programmer, what is important is like he or she will simply calculate that I am doing n addition. So this is addition. So I am doing n addition. So I am doing n flops, n floating point operations. So let's assume that B and C can be anything. It can be a single precision or it can be double precision. However, a computer architect will look into it in a different way actually. So the computer architect will look into like how many instructions are being executed to really achieve these n flops. So that there can be several instructions. There can be load, store, execution. Okay, so whatever. So there are two different viewpoints. So programmer is always interested in how many flops is being performed. Computer architect, it's more details actually in the instructions. He or she is more interested in the instructions. Now the second question is how much data transfer really happened in this simple code actually. So if I look into one loop, one instance of loop, then there is, let's say, 8 byte for each variable. Let's say 8 bytes each. I mean A, B, and C. So total is like 24 bytes. That is for the per iteration, I will say. Okay, so per iteration. Okay, now if you have n iterations, so you will have 24 n bytes. Okay, so and how do we measure this? So this is like if you're interested in rate, then you will be interested in how many bytes per second. So that's what we are interested in, or how many bytes per cycle, whatever. Yeah, I mean, so let me write it down second now. So the measure here is how many bytes per second or per cycle, and the measure here, that is the total work, is how many flops per second. Okay, and these two are the important things which contribute to the total runtime. So that was one discussion which we had in our previous lecture. And the second important point was the classification of computers in four different categories, that is SI, SD, SIMD, MISD, and MIMD, based on the instruction stream and the data streams. And these more details can be found in this paper, some computer organizations and their effectiveness by M.J. Frink. This was published in 1972. So that briefly summarizes what we did in our previous lecture. Now, in today's lecture, it's very important to really understand the effects of the architecture on code actually. So today we are going to look into a particular code which we call benchmark. We'll come there and to really understand how really architecture plays an important role in the performance or the total runtime of that code. Okay. Now, these 2 points we have already discussed that typically von Neumann architecture has three components: memory, CPU, which has both the things, I mean, ALU and control unit, and then the interconnection actually, so the data path. And then there is a von Neumann bottleneck, which is primarily because of this memory limitation. And two important modifications which has been done, I mean, over the years. One is the caching, and the second is the pipeline. In addition to these two important modifications, there are some other improvements which has been also done, which we'll also discuss gradually. But before we go there, I mean, if you're trying to understand the effect of architecture on a code, so first we should understand what we are going to get from the code and how we can interpret that. So one thing we all know, I mean, even we discussed in the first lecture that all components, not only the computer, all components of a computing system can operate at some maximum speed, and that is what is called peak performance. So you have a peak performance of a memory, you have a peak performance of the processor. So whatever components you have, each of them has some peak performance. Now, the important point is how do we know that how much our code is really utilizing the peak performance of each of those components, like whether my code, it's possible that my code is probably doing a good job in achieving peak performance in terms of CPU, but may not be doing a very good in terms of the peak performance of the memory units. So there are two important quantities which we typically use to measure the performance. One is the compute throughput, so that is measured in gigaflops per second, and the second is the memory bandwidth, so gigabytes per second. So today we are going to discuss a very important benchmark, which we call low-level benchmark. So what are these benchmarks? So these are actually simple programs that tries to test some specific features of the architecture. So primarily the memory units and these ALUs actually. So what it does, it basically isolates small set of instructions to separate influences and determine specific machine capabilities. So what is the capability of the memory system? What is the capability of the processor and all? So we are going to look into a benchmark, such a benchmark, a low-level benchmark, which we also call micro benchmark. And this is a very popular micro benchmark, which is being used in both academia as well as industry to test architectures actually. So what it basically does is like it's a simple program which has a multiply and add nested loop, and it is done on three vectors. Okay, so first let us look into the code actually. Okay, so this is a typical vector triad code. Triad. Okay, so at any point if you find any difficulty, just stop me and ask me. So what it does is basically you can see you have this B and C vectors, and then there is another vector D. So you have one addition here and one multiplication here, and then you are storing it in A. That's the typical vector trie. Now, how this program is written, that you have to understand very carefully. Okay. So first thing is that you are initializing something called size, minimum size. So that is like 2 to the power 3, and maximum size 2 to the power 29. And then you are saying the total, you are introducing a new variable, total is equal to maximum size. So total is basically 2 to the power 29. So let me write it down here. Total is equal to 2 to the power 29. Now, you're starting your first for loop. So you can see your size is basically changing from 2 to the power 3 to 2 to the power 29 by a factor of 2. So that's your for loop. So this for loop looks like for let's say s is equal to 2 to the power 3 to 2 to the power 29, and then you are initializing your variables, and you can see whatever is the size. So initially the size can be say from if the minimum size is 2 to the power 3, maximum size can be something, because this whole thing is inside this loop actually. The whole thing is inside this loop. Let's say the first time this is running from first instance this is running from 2 to the power 3 to 2 to the power 4. Okay, second time again it can run from 2 to the power 3 to 2 to the power 5 and so on. Okay, now you are first storing this value. So bi is equal to 3, c it is a constant. I mean all the b's are 3, all the c's are 2, and all the d's are 1. Now what you are doing, this is the important point actually, that you are introducing a new variable runs. Okay, and then you are saying the runs is equal to total divided by size. So what does that mean? That total is fixed actually. So this you have already fixed, is total is equal to 2 to the power 29. So therefore, as your size, as this size actually increases, the runs will decrease. Okay, so this part is important. So as size increases, the runs will come down. This variable will come down. However, the runs into size total remains fixed actually. So therefore, you can see that we are using these two variables here, this runs here and then size here actually. So what does that mean is that if we combine these two for loops, they will always execute the same number of iterations, because runs into size is equal to total. Okay. Now what we are doing, we are first running this run loop from 0 to runs, and this another. So this is the vector trad part. So vector trad is equal, a is equal to b plus c into d. So that is being executed here. So you can see b plus c into d. Okay. So if I look into this code carefully, so this particular item, this particular instruction, I mean a is equal to the vector trad, basically a is equal to b plus c into d, is executed total time. Okay, so this is particularly executed total times, but only difference is that in some cases this loop will execute more compared to this, and then gradually, this will keep on increasing, because your as your size, because your outer loop is size, so as size increases, runs will go down, so this outer loop will decrease, and then your inner loop will increase actually. Okay, now this part, if you look into this part, you can see this is something which is never true. Okay, something which is never true. Okay, now why do you do that? Why do we place this particular thing here? Is that because sometimes what happens, these compilers are very smart. So compiler will actually realize that you are actually there is no use of this loop actually. This outer loop, there is no use, because you are actually calculating a is equal to b plus c into d, and a, b, c, d, everything is constant. So it will not even do it several times. It will just do it once times and get out of this loop. So just to force the compiler that you really complete this total time actually, you run both the loops completely. We just put a function here and put a condition which is never true, or that will force the compiler to really run it the expected number of time. The number of times we really want to run both these loops. And another important thing what we should notice here is that we are putting a timer here. So that is like a start. So you are using a clock here to note the start time of this program, and then you are using another clock here, which is the end time of the program. So the difference between these two times, end minus start, will give you the total time to execute this part actually. That is what we are interested in. Okay. And then you can get it in wall time by using these clocks per second. You will go into the details later on. And our job is basically, our goal is basically to calculate the throughput. That is how many flops per second our code is achieving on a given architecture. So I can see that as a programmer, for me, what is important is how many operations I'm basically doing. So I am doing two operations, one plus and one multiplication. So I'm just taking two here, two. And then how many times I'm doing it? I'm doing it total times. So I'm putting my total here. Okay. And so that's my total operations. And then I divide it by time. So that will give me floating point operations per second. This part is clear to all of you?
Sir, where does that starting loop ends for int
Yeah,
size?
yeah, yes, that starting loop ends somewhere. So that's why I just kept it open actually. It ends somewhere, it ends actually. That's a good question. I mean, that ends. I'm not so neat explicitly because I can add couple of other instructions here.
Okay.
Okay. Yeah, but the point is the starting, there is a starting loop which is the outer loop actually. Yes. So everything is clear.
Hello, sir. Your screen is lagging.
My screen is lagging. All of you are finding this difficulty?
Yes, sir.
Yes, sir.
Yes, sir.
But you can see my screen right now, right?
Yes, sir. We can see, but it's lagging. So whenever you're writing, we cannot see it immediately. It appears
Okay.
sometime later.
Okay. So that's the problem of the network. But overall now it is clear, right, to all of you? Okay. Now I will ask a question actually. Now, if I look into this, if I want to plot, I mean, let's say I want to plot. Okay, I want to plot something, and in the x-axis, I basically want to put this size here. This size I want to put here. Okay, and in the y-axis, I want to put this one, this throughput. So I want to put this performance. Let's say performance. Yeah. So what kind of curve I should get? Uh, Before even I go to that question, the number of computations which I'm doing inside this outer loop actually. So inside this outer loop, whatever number of computations I am doing, that is fixed or not for all sizes.
Yes, sir. It is fixed.
It is fixed. All of you agree, right? This is fixed because finally these two loops, because total is equal to runs into size. So that's the important point. That totals here, total is equal to runs into size, and I've already fixed my total here. So this total is always going to be the same actually. Okay. Now, so basically what we are trying to understand is that whatever size you take here, you are exactly going to do the same number of computers every time. Now, if I plot this throughput, which is like number of computations divide by the total amount of time. So what do you think? The time will be same for all the iterations, or it will be different?
It should be same.
Same.
It should be same. So it should look like this, right?
Sir,
All
I
of you
think
agree?
it can decrease because we are accessing more part of memory.
It can
No, it
decrease.
should be straight line only.
Yeah, I mean, if it's an ideal world, then what is whether it should be straight line or not? Ideal world.
It should be
Then
Straight
it
straight
will
line.
be
line.
straight line.
Straight
Yeah,
line.
if it is an ideal world, then it should be straight line because finally, what is happening is like I'm just changing my loops. That's all. But overall, if I just look it from a programmer's perspective, then I'm doing the same number of operations every time. It's just that I'm changing the loop counters actually. That's all. In sometimes this loop, so basically this runs loops is actually decreasing, but this is again increasing correspondingly. So the total number remains same. But when I run it, you can also do it in the first assignment. You are actually supposed to do that. You'll get something like this. This is actually from that lab 207 message. Okay. So this is what you will get. So you can see that if you change the loop length actually, so the outer loop actually, if you change the outer loop, so as it increases, so that's I call it problem size. then the throughput which you get is like something like this. Okay, you can see my screen, right?
Yes, sir.
Yeah. Now, whenever you see this kind of curve actually, and you try to interpret it, that is very challenging in the sense that it's not a very linear trend. I mean, you can see several things here. It's not a very kind of a simple linear kind of thing that you can interpret it easily. So whenever you see this kind of curve, the first thing you should do is like you divide it into several zones, and then you try to explain it zone wise. So one thing I can see that there is some behavior in this zone, then there is some behavior in this zone, there is some behavior, I mean somewhere here you can see some behavior. Overall here there is a typically a different kind of behavior, because if you look from this point, then it is really coming down actually. Always it is coming down, I mean, then it's also it's typically a downward trend. But here this particular point there is a upward trend actually. Okay, yeah, I mean you can say that there also there is a little bit of upward trend, but that's actually, if you smooth it, actually typically the trend is actually downward, I mean overall, except in this part where it is little bit upward. Okay, so our job is really to understand why we are getting this curve, because if it is an ideal situation, then I should get a straight line, because I am always I am doing the same number of operations. So ideally it should take same amount of time. Why should it really change depending on how I place my loops actually? Okay, so that's the thing we are going to understand gradually. I mean how the architecture plays an important role. Overall, this part is clear to all of you.
Yes, sir.
Any questions at this point of time? Okay, now let's say that I also want to calculate the memory throughput. So this is the compute throughput. So this is the throughput is compute throughput. Now if I want to calculate the memory throughput, I am writing it memory throughput. So then what should be the formula for that? What is the unit for memory throughput? I think
Gigabytes per second.
exactly, gigabytes per second. So the formula should be written in such a way that it comes in that unit actually. So that the denominator is going to be same. I mean it is going to be the, I mean it is going to be the wall clock time. So the denominator will be wall clock time. So that wall time. Okay, and what will come here? How many data we are accessing, right? How much data we are accessing, right? So how much data you are accessing in this particular region, that is A equal to B plus C into D? How much data you are really accessing?
Sir,
Four,
total into
four,
4.
4 into 8.
Let's
4
assume
into
that there are yeah, let's assume that it's a double precision, so 8 bytes. So then it is 4 into 8, right? All of you
4
agree?
into 8. Yeah.
Yeah, so that will be like total into 4 into 8, and that will be bytes, and that will be like the total memory throughput. So we can also put we can also plot similar curve for memory throughput. So this curve is for the compute throughput. So you can see the unit is actually it will be unit is gigaflops per second. So I can draw a similar curve for memory throughput, which will be gigabytes per second, and it will be interesting to see how that curve looks like. I mean, you should do that. And the x-axis will be the loop length. Okay, so it's not very easy to really to interpret this plot actually, but we'll do that after we understand a couple of things. Let me summarize this plot actually a little bit. Um, so the summary is that typically, if you look into loop-based code actually, so most of the codes are actually loop-based codes. Large amount of data movement in and out of the CPU. So CPU is basically the ALU and control unit. So large amount of data movement is happening. Concern is underutilization of on-chip resources. So this must have happened because of some reason. Otherwise, I should have simply got a straight line. But yeah, and you can see this is a big drop actually, because it is here it is around 30, and then here it is around I mean 5. So that's like a 6 times drop, which is huge in fact. So it is like one order. I mean, one order is 10 times, so more close to one order actually. So something is going wrong. I mean, so that we need to understand. But as such, if you look into the code, there is nothing wrong actually. So it's perfect actually, the observation. Several data paths, so that we need to understand. So the several data paths leads to range of bandwidths and latencies. Okay. Now the objective is, can we reduce traffic over slow data paths? So something must be happening that the slow data paths are coming into the picture, and that is uh, bringing the overall performance down. And that's where the optimization comes into picture. How can we reduce traffic over slow data paths? So this is a little bit of summary regarding micro benchmarking. So micro benchmarks are small programs which are used for probing memory hierarchy, to understand the saturation effects in cache memory and typical overload. So saturation is, you can see, these are like saturation. So sometimes it saturates and then again come down. Okay. Now, if I plot this trend overall, this trend actually, so here you can see the years actually. I discussed about von Neumann bottleneck. So what is that? Or we also call it memory wall. So what is that really? So if we put time in the x-axis, so this is my time, and if I put performance in the y-axis, so in this performance you don't see a unit here, because the y-axis is common actually for both the memory throughput as well as the compute throughput. So that is compute performance and memory performance. Now, if you look into the compute part, so that is this line actually. You can see CPU here. So that is this line. You can see that it is almost following Moore's law. Okay, but if you look into the memory part, the memory performance over the years, how it is improving, you can see that initially more or less they started at the same point actually, and then as time is progressing, this gap is actually increasing. This gap is getting bigger and bigger actually, and this gap is actually called DRAM gap. This gap, yeah, so this is called DRAM memory gap. So you can see the microprocessor performance is increasing almost 2 times per 1.5 year as per Moore's law actually. But the DRAM performance, that is the memory performance, is only it takes almost 10 years to get to 2 times. Okay, so it clearly tells that if you really want to write optimized code, you have to really address the issue of memory, the data flow actually, the data path. I mean, that is where the skill lies actually. How you can reduce this part actually, how you can reduce where is that yeah, how you can reduce traffic over slow data path by modifying your code. It will still get the same result, but just you will modify the code and whatever code you are working with. Okay. Now let's understand the latency and the bandwidth part here. So this is my bandwidth and this is my latency. Uh, let's first understand what is latency. Okay, so latency, as we know, the unit is actually in time, so seconds. Okay, so it is almost like, suppose you want to make a mobile phone call, you always have to wait for a small duration of time before your call gets connected. So whether you talk for 1 minute or you talk for 1 hour or you talk for 5 seconds, that time will be same. So the connection time. So that is the minimum amount of time which you have to spend before even you can start your phone call. And exactly the same logic can be applied in understanding latency. So latency is something like the minimum amount of time which should be spent before the first byte of data actually starts moving. So that is called the latency. And the bandwidth is actually the rate at which you are transferring data. Okay, now if I look into the core actually, the processor, or you can say inside processor there can be several cores. So let's look into the core picture. So if you look into a core, so you have these functional units, ALUs and all. So the closest to the ALUs are the registers are sitting, which are very small actually, very small in size. and then you have L1 cache, and then you have L2 cache, then you have L3 cache, and then the RAM actually, and then you have hard disk. Now, if you look into the bandwidth, you can see the bandwidths are very different. So if you look into L1 cache bandwidths, it's almost like this is actually an old figure. I will show you the latest one actually. But what is to be really understood from this figure is that there is a significant decrease in bandwidth as you go away from the functional unit. So as we are going away from the functional unit, so the distance, because finally the most of the data is in probably in disk or in RAM actually. So from there the data has to flow, and then there is only one way it can flow. So from memory it has to first come to the cache, and from cache it has to come to the registers, and then it can go to the functional unit actually. And so it has to go through several data paths, and we can see that each of these data paths has different bandwidth and different latency. So if you look into the latest, I mean, more complete diagram, so that tells you the complete latency bandwidth picture in a modern computer environment. Okay, so what are the important data paths? So there is this inner cache is there, then there is outer cache. In some special processors like GPUs and all, you have this high bandwidth memory is also there. Then you have this RAM, which is the main memory. Then you have high performance computing networks. Okay, those switches and all. Then you have this 10 gigabit Ethernet. Then you have SSD, solid text disk, and then you can have gigabit Ethernet and local hard disk and internet. Now you can see on the left side. So on this side you can see the units are in nanoseconds, microsecond, and milliseconds. So that is in seconds actually. So when your data is in the inner cache actually, then it's very fast actually. The latency is only 10 to the power minus 9 seconds. So latency is the minimum amount of time you have to spend to give this data to the ALUs, the logical units or the execution units actually. And at what rate you can get the data, so that is on the right hand side. So that is the unit is gigabytes per second. So that's the bandwidth. So you can see that if I have to get data from the main memory, this main memory, so typically I get it at around 10 to the power 11. 10 to the power 11, between 10 to the power 10 to 10 to the power 11. But if the data is already sitting on the cache, then I can get it at a much faster rate. I mean, it is, you can see it's almost one order faster actually. And if your data is sitting in the hard disk, then it's very slow actually. You can see it's 10 to the power 9 actually, 1 gigabytes per second. And also the networks also play an important role. So you can see the networks, if it is HPC, high performance computing network, so still you can get it at 10 gigabytes per second, but otherwise it is 1 gigabytes per second. I mean, this typical 10 gigabit Ethernet network. And so this overall summarizes the overall memory picture actually, that we have to optimize in both the sides. So there is a latency and then there is a bandwidth, and these are the important issues. How to avoid slow data paths, because that's the most important technique to learn to optimize the performance. And how slow are these data paths, so that quantitative understanding we can get from this picture. This part is clear to all of you?
Yes, sir.
Okay, perfect. So before we go ahead, let me quickly summarize. So the first summary is that there are micro benchmarks, which are typically small programs which can be used to test the architecture. Second important point is that when you really deal with today's modern computer environments, you have to deal with several data paths. I mean, in this picture, you can see almost like 10 different data paths. I mean, starting from internet to the L1 cache. And we really need to make sure that we reduce the traffic over the slow data path. Unless we do that, we'll not get the best performance. And a couple of important units to always remember is the bandwidth, bytes per second, the compute throughput, which is flops per second, the latency, which is in seconds. These are three important terms. Okay. Now, let me introduce a new term actually, which is called the code balance. Now, what is code balance? So, code balance, we use this term for typically for the loop actually. So, how much uh, is the data traffic and how many floating point operations you are doing? So, let me just write a loop here. Do I is equal to 1 to n, ai is equal to bi plus ci, and then end. Okay. Now here, if I ask you what is the code balance of this loop, so what is the code balance of this loop? So what is the unit of this data traffic?
Bytes.
Gigabytes.
Bytes.
Bytes. Okay, this is bytes. Okay, and what is the unit of this floating point operations? Flop, right? Okay, so the final unit which we'll get is like bytes per flops. Let us just keep this in mind. So what we are saying is bytes per operations. Bytes per operations. So that is called the code balance of a loop, or you can even say if it is that's the whole program, then you can say the code balance of this program. So here, if you look at it carefully, depends on whether it's floating point or I mean single precision or double precision. You can see we're just doing one operation, so it is like one operation, and then how many bytes you are I mean you are taking to achieve that actually. So you can see two load and one store, so that's like 24. So the code balance here is like 24, and the reciprocal of code balance, so that is like we call it computational intensity. So here the unit will be flops per bytes. It's the opposite, flops per bytes. So how many floating point operations you are doing on on the amount of data which you are fetching from the memory. So when you're talking about data, we are talking about load, store, and execution of operations. So basically, primarily load and store of that particular code. And the data traffic is the performance limiting data path. So this is hardware dependent from where the data is coming. Now, so the point here is that there are several data paths, and typical bandwidth and latencies are different for each of these data, because when you are writing this, even this simple code, because finally the data has to come from the RAM actually, the B, C, everything has to come from the path is always same. I mean RAM to the outer cache, and then gradually to inner cache, and then to register, and then finally to the CPU actually. So this is called actually the balance analysis. So let me write it down here. This is called balance analysis. Okay. Okay, this part is clear. This part is clear.
Yes, sir. I have a doubt, sir. How
Yes.
data traffic is different from data? Means the given example of AI is equal to BI plus CI.
Mm.
So
Mm.
can we calculate the code balance from this given data, or should we be having
Yes.
some more data to it?
Yeah. That's a very interesting question actually. So now we have to go little deep to really understand. Now that depends on what is the value of n. Okay. Now let's say not only the value of n, it also depends on whether you have another outer loop here or not. So because if you look into this picture actually, if this picture, so you see, if you're just playing around with say 1 GB of data, couple of gigabytes of data, then the RAM is fine actually, so you can load the whole problem on the RAM. But suppose you're really working with a very big problem actually, big data problem, so the whole data cannot be loaded on the RAM, right? So finally it has to come from the SSD or from whatever hard disk you have. You got it, right?
Yes, sir.
Yeah, so it all depends on the code which you have written, how much data it is going to utilize actually, because this code which I have shown here, this simple code, I mean this n can be anything. This n can be a simple 1000, or it can be 10 to the power 13. The moment you are talking about 10 to the power 13, I mean, so then you can imagine what is the size of your B and C actually. Got it, right? So even
Yes.
if your even if your n is say 10 to the power 9, so the B each of these arrays are actually of the size. Let's say it is 8 bytes, so that's like 8 GB each array. Okay, so basically you're dealing with a 24 GB problem. Data structure, the size of the data structure. This part is clear to all of you, right?
Yes. Yes, sir.
Yes. Now this is a very very programmer's perspective. I mean, code balance is something. If I give this program this simple code to a programmer, he or she will basically calculate the code balance. Okay, but this code balance does not tell anything about the machine actually. So it is irrespective of on which machine you are going to run this code. I've simply given you a code. You just look into this, that how much data I have to read and how much operations I have to do, and by using this formula you can tell me what is the code balance of the loop or what is the computational intensity, which is just the reciprocal of code balance. Now comes the second picture, which you called the machine balance. Now, what is machine balance? So the machine balance is, this is the formula for the machine balance for a given machine actually. So the machine balance is memory bandwidth divided by peak performance. Okay. Now, what is the unit for memory bandwidth?
Bytes per second.
Bytes per, bytes per second. Bytes per second. Bytes per second. Yes. And what is the peak performance? What is the unit?
Flops
Yeah, flops per
per second.
second. Now, what do you get? Bytes per flops, right? Now, if you look into your code balance, what is the unit of code balance?
Bytes per flops.
Bytes per flops. Yeah. So bytes per flops. Now, now what you have started doing is like you are doing both. You are doing code balance and you are also doing machine balance. So now you are doing some kind of connection between your code and the machine on which you are going to run that code. Now, generally, what happens is like you have a given machine. Every time you do not change your machine, right? So you have your own laptop or whatever desktop. For that particular machine, this is fixed. I mean, this number is fixed. I mean, what is the memory bandwidth of that machine and what is the peak performance? Now, when you change from algorithm to algorithm, like application to application, so when you are doing a, so let's say a vector addition, so that is like a vector addition, you can see that it will have some kind of code balance. The moment I go from vector addition to vector triad, it will have some other code balance. The moment I go to matrix multiplication, it will have some other code balance, but the machine balance remains same for your machine. Because your machine is fixed unless you change the machine itself. This part is clear to all of you? This part is clear?
Yes, sir.
Yes, sir.
Yeah. Yeah. So the machine balance of a processor. So this is I'm clearly saying the machine balance of a processor chip. The machine balance of a processor chip is the ratio of possible memory bandwidth, that is in bytes per second, to peak performance in gigaflops per second. Okay. And we typically the notation which we use is b underscore m, and here for the code balance we typically use b underscore c. And interestingly, both have same units. So unit is bytes per flop for code balance, which is more like a programmer's perspective, and the machine balance is more like an architecture, the what is the machine balance of a processor or the machine itself, which is again in bytes per flops. Okay. Now these are very useful because most of the time, I mean, there are actually different kinds of codes actually. So I will go there later. Like some codes are memory bound code, some codes are compute bound code. So generally what happens if I give you a code, let's say I give you matrix multiplication, then first thing you have to understand what your code falls into which of these categories. Whether your code is a memory bound code, your code is a compute bound code, or it falls somewhere in between. Or I ask you that you are working on a Monte Carlo algorithm. So whether it's a memory bound algorithm or it's a compute bound algorithm, so that tells a lot actually. I mean, how one should approach the problem actually. And what are the typical bottlenecks. I mean, if you want to optimize your course, the first thing to be done is like to figure out your algorithm falls in which category, and then do some balance analysis, which is this. I mean, whatever machine you have been given, and what is the code balance of your code, and whether there's a match between those two things or not. Okay, now let me just play around with some numbers. Let's say what is a typical for, let's talk about one core. So what is the typical this denominator peak performance for one core? Yeah, peak performance for one core. Can someone tell me?
Sir, 4.
No,
Sir,
I mean,
about 10 gigaflops.
perfect. 10 gigaflops, around 10 gigaflops per second. Okay, we did that calculation. So always remember, to get this number, you have to take the processor frequency, which is in cycles per second. Then how many flops that can do your microprocessor, which can be 248, whatever, not a very big number, typically 248. That is a number of I mean flops per cycle. And then here we are talking about one core, so we just put one, so you'll get typically if you have a 2.5 gigahertz processor and we assume that it can do 4 flops per cycle, so then my core this peak performance is 10 gigaflops per second. This part is clear to all of you, right? Once again I
Yes, sir.
will, because yeah, so once
Yes, sir.
again I will write, yeah, so I'm just writing it here, 2.5 gigahertz into 4 flops per cycle, and I have one core, and that will give me around 10 gigaflops per second. Okay, now so I got this denominator which is fixed actually. So for a given machine, this is fixed 10 gigaflops per second. The moment I change this data path actually, so now if I go to catch, let's go back to the picture. So what number I should use for, say, let's say a catch? Typically, what number I should take? Once again, I will repeat the question. So I'm looking for memory bandwidth. I'm looking for the numerator now. So numerator is memory bandwidth. So what typical number I should use if I'm considering cache memory?
Main memory maybe.
The
Or
cache
outer
memory.
cache.
Yeah.
Outer
So
cache.
what is the number? What is the order I should use typically from here,
64.
from this?
10
Gigabytes.
raised to
100 giga.
Yeah, 10 raised to
No,
11.
10 to
10
the
raised to
11.
11, yes.
100
10 raised to
gigabytes.
11. 10 raised to 11, somewhere here, right? So you can see this
Yes.
is like the outer cache is somewhere. So if this outer cache is connected here, okay, and even the inner cache is somewhere here. Actually, here this is the inner cache. So that's around 10 to the power 11. That makes a reasonable number. Yes, I'm just doing an approximate thing, so I can put 10 to the power 11 here. Not balanced actually. So I'm putting here actually the bandwidth. So this is 10 to the power 11. Now, if I go to the RAM, what should I write?
8 GB or something.
No. The bandwidth, bandwidth, the unit of bandwidth is,
10 to the power 10 maybe.
yes, 10 to the power 10. I mean, if you look into the memory, so that is this line actually. So this almost stretches down to 10 to the power 10. Typically, this number actually, and the unit is gigabytes per second. Okay, so once again, I will explain this curve. On this curve, the y-axis is bandwidth, which is bytes per second. Sorry, the right-hand side, and the left-hand side is latency, which is in second. So what we are saying is that these are the typical memory components, or memory in the sense typical components from where data is fetched, and each of them has different latency and different bandwidth. So the fastest one in terms of bandwidth and latency is the inner cache, and then gradually the slowest one probably will be the internet. So here what we are doing is we want to understand this balance actually. So what we are saying is that given a machine, so I have already told you that I have given you a machine which is 2.5 gigahertz and 4 flops per cycle and one core. So you have already finalized your denominator. Now for each
Yeah.
of these memory, I want to get the numerator.
Number.
So okay, so for the numerator, first I looked into the cache, so I can see the cache is the bandwidth is typically sitting somewhere here, and the RAM somewhere it is sitting here, and let's say the third one is probably let's say internet. Oh, this is interconnect. Let's say disk, hard disk. So let us just do the three: cache, RAM, and hard disk. So where is my hard disk sitting here? Let's say solid state disk. Okay. So typically I can use 10 to the power 9 here. Okay, so let me
Yes.
just write down this number. So 10 to the power 11, 10 to the power 10, and 10 to the power 9. So what will be the I mean the machine balance for this particular thing?
Summation of all this. Plus plus 10.
No, not summation. You have to calculate it individually. So what is the machine balance for cache?
Okay, 10 is power 11 by 10.
10. It's
Just 10.
10. Yeah.
Yeah.
And
10
what is
bytes
this
per
for the
flops.
RAM? Yeah, exactly. And what is the RAM for this data
1.
path?
1.
1.
1.
Yeah, and this
1
yes,
upon 10.
0.1. Now, see, just look into the importance of this number, how important this number is. So it very much depends, I mean, from where you are fetching your data. Now the point is, suppose you are, I mean, you are working on some code, let's say the code balance of that code is, let's say 1. Let's just assume the code balance of a given code, whichever code you are working on, is 1. And you are getting data for the, I mean, the memory bandwidth for the machine, whatever machine you are using is 0.1 for whatever reason. Then what will happen? So there is an absolute mismatch, right? So your code wants to get your code has a code balance of 1 bytes per flops, and your machine balance is low actually. Machine balance is 0.1. Let's assume that because of some reason it is 0.1. And the problem is machine balance will decrease in future actually. If this is a question, machine balance will decrease or increase in future. So what will be the answer? What should be the answer for this?
And constant.
No, it will not remain constant, because what is happening? Your peak performance is continuously increasing, right?
Okay.
Yeah, because this peak performance is coming from your processor, and we can
Yes,
see that
yes,
we are,
yes, yes,
yeah.
yes. Yes,
So what is
yes, yes,
happening?
yes.
Yeah.
Yeah.
So what is happening is that
It
your
will decrease.
exactly.
Yeah.
Yeah, your this machine balance will keep on decreasing in future because you're introducing more and more core. So the moment you increase more and more core, your peak performance of your computing system will go up, but you are not doing the similar progress in memory bandwidth. So overall the machine balance will decrease in future, and that's the historical trend actually. So that is exactly what is happening here. Here also I can see that trend actually, that there is a gap which is coming actually. So the point is, whenever a code is given to you and a machine is also given to you, so we should do some kind of analysis, I mean, in terms of the machine balance and code balance, and see, I mean, how close or how far they are from each other. So ideally, I mean, if I have to write it, let me write it down. So let's write a good code actually. Let me say a good code. So uh, whatever, because BM is fixed actually, because the machine is given actually. Machine is given. You cannot change the machine. You have already. So good code has a small code balance or a higher code balance. Let's say this is my BC. So code balance. So uh, what should I aim for? A good code should have a higher code balance or a smaller code balance?
Smaller.
Higher.
Yes, it should. No, it should be smaller. It should be smaller, not higher. Okay, why it should be
Just
smaller?
to
Now once again go back here.
machine. Yeah.
Machine balance is fixed.
Yes.
Machine balance is
The
fixed because
ma-
once I have given you the machine, so let's say there is some machine which is there in lab 207. I mean, I cannot keep on changing the machine for every algorithm. So that's fixed, right? I mean, you have a machine which is there for 3 4 years. So machine balance is something which is like, so these are fixed. Like you have some cache, some RAM, some disk, whatever they have their peak performance. So that is fixed for a given machine. Now what I am saying is like, my question is good code. So some good application, what I should expect? I mean, if I want to develop a good optimized code, I mean, in which direction I should go? So this
Less
should be
memory
definitely
access.
exactly less memory access. So less memory access means the code balance should be
Less.
small. Exactly. So
Yeah.
because the code balance is actually bytes per operations or bytes per flops. So you should get less data and you should do more and more operation on that. Okay. And so the point, I mean, we'll go there gradually, but the point is that what I can see here, if I have got some data into my cache, before I throw it from the cache, I should ensure that whatever job needs to be done on that data, first do that before you throw out or flush that cache actually. I will come there gradually when you discuss about algorithms. We discuss this point in a very detail when you do matrix multiplication algorithm. But overall, this is important learning that ideally we should see how. I mean, so basically, what I'm trying to tell is that BM by BC will increase for good loops. So you have a good. So suppose you have loop. So for good loops, this should increase actually. This is clear to all of you.
Yes, sir.
yes.
Okay. We'll come to, I'm just giving a very brief introduction now because when we'll go to the real algorithms, I will go into more details of these things. Okay, so till now, this point, I think we have understood what is a simple benchmark. After we done that vector triad, we got something which was very unexpected. I mean, non-intuitive as well. This result was not at all intuitive. It is very non-intuitive result. I mean, ideally, I should have got a straight line. So one really needs to understand why this is so. So that will take couple of lectures to really understand that. Now couple of other things what we should look into now is like, suppose I want to optimize the code, how should I go ahead? I mean, what are the steps to be followed? I mean, first couple of steps. So there is no alternative to knowing what is going on between your code and the hardware. So we need to do performance modeling. So the only way to really optimize your code is to understand what is going on inside your code. And for that, what we typically do is called profiling. Okay, so you use profilers. So profilers actually are some kind of libraries which are already there. I mean, there are commercial profilers, there are open source profilers. So a very popular open source profiler is gprop, which is called GNU profiler. So this is from GNU, gprop. It is already installed in the machines, which has been you have already been provided access to the machines. So what this profiling does is like it gives information about the program's behavior. So let's say you have a program which has several subroutines and functions, etc. A lot of subroutines, let's say S1, S2, S3, you have several functions, F1, F2, F3. So first thing really to we need to understand what is going on inside that subroutines and function. Which subroutine is taking more time? Which subroutine is being? Which functions are being called more compared to other functions? And then we have to identify what we call hotspots in terms of runtime. So sometimes what happens? Let's say you have 10 subroutines, and maybe the 90% of the time is being taken by the first two subroutines. So if you want to optimize, first you have to attack those first two subroutines, S1 and S2, let's say. I mean, if they are taking 90-95% of the time. So that is called the, and even in that subroutine, there can be some particular, I mean, operations or some particular lines in those subroutines which might be taking the maximum amount of time. So we need to really identify which are those hotspots, and then only we can optimize. So first is like identifying hotspots. So what helps us in identifying hotspots? A profile. Okay. So so once we go get these hotspots, these are called performance bottleneck, and then we can think about optimization. So we learn about some of the well-known optimization techniques actually. I mean, if that kind of uh, limitation is present in your code, how what are the techniques to be used to remove that limitation? And there are two kinds of profiling. One is called function profiling, and the second is called line-based profiling. You will simply use a profiler. Will not go into too much details of how those profilers works and all. What is important for us is to realize what is the output of that profile. Okay. So typically, I will just show you some output from a simple exercise which I have done. So what you have to do to run this profiler, what it does is it gives you a breakup time. The profiler, the output of a profiler will show you the breakup time taken by each subroutine or functions of the code. So if we are using a GCC, I mean a C code, then you can just replace this F90 with GCC. Okay, or if you are using for ICC, I mean Intel compiler, you have to use a different profiler. So let's say that you are using a GNU compiler GCC, and then you use this flag minus PG, and then this is the file name. So in this case, if you are using C, so this will be file.cc or CU, whatever. C actually for C proper. For CUDA actually we use this CU. Uh, After running the executable, so once you generate the executable, a.out will get a file called gmon.out. So the moment you do that, you will get this gmon.out. So you have to give this command. So you just give gprop minus minus line a.out and then this gmon.out, which will be created before you give this command. And once you do that, you will get something like this. Let me see. Yeah, you'll get something like this. Yeah. So this is the output. Okay. Now this is from a typical code. From one of my code actually. So in that code, I have some subroutines. So this is a subroutine. These are subroutines or functions, whatever they are. Okay, so these are the typical ones. So I found that originally it was taking 39.86 seconds, and then if you really look into that, then you can identify that which subroutine is taking maximum amount of time. So it turns out that this first one, so this is actually when you look into the output, this is I mean, you will see it in order actually, in order in terms of the percentage time actually. So you can see that 50% of the time is actually taken by this subroutine, around 25% of the time is being taken by the second subroutine, and then another 10% by this. So you can see these subroutines are not subroutines or functions. They are not taking the majority of the time. Majority of the time is taken by this subroutines. Now, once you have identified that these are the subroutines or functions where I really need to optimize, then you learn the optimization techniques. Most of them are related to data access, and then you change some. You change your code. You change some specific things in your code. I mean, you rewrite the code in certain way, and then you will see that everything will change. So now this is a new code. So after I got this output, I made some change based on my understanding of optimization. I got a new code which is now taking 26.59 seconds. So you can see there is a significant, decrease in the runtime. So from 39, I mean 40 seconds, it came down to almost 25 seconds. So almost like a 15 seconds reduction. And now you can see that there is a significant, improvement in some of the subroutines actually. Okay, so the first lab actually you have to really understand the outputs. I mean, what does that mean? So that we will do. Any question at this point regarding this?
Sir, I don't know. I didn't understand about the subroutines. So can you explain again?
Yes. So let's say you have a code. Okay, let's say you have a code. This is my code, a big code. So I can have one subroutine. You have written C codes earlier, right?
Yes, sir.
Yeah. So let's say I have some subroutine A. Okay, inside that subroutine, I call a function B. Okay, and then inside that subroutine A, I can also call subroutine B. Then I have another subroutine which is C. So generally, when you look into an application, you can have several subroutines inside that application, right?
Yes, sir.
Yeah. So that is what I'm telling here. So I'm saying that I have a code. I have a code which has 1, 2, 3, 4, 5, 6, 7, 8, 9. I mean, you can remove this main actually. So let's say 1, 2, 3, 4, 5, 6, 7, 8. 8 subroutines or functions are there. Now, I really want to understand which subroutine is taking the maximum amount of time. Got it, right?
Yes, sir.
Yeah.
Like in the
Yes.
first code, the subroutine named adv dot underscore, it's taking more time, right? Like
Yes.
it's equal to 19.47 seconds.
Exactly. It is taking 19.47 seconds, and in terms of percentage of the total runtime, it is taking around 50%. So 50% of the time is just being taken by this first subroutine. Okay.
Yes, sir. Understand.
So, yeah. So this is called the hotspot. So if I have to really optimize the code, first I have to address the issue in this subroutine. Because if this subroutine is addressed, now we can see that from 19.47 seconds, you have got it down to 14.04 seconds. The same subroutine in the new code, right?
Yes, sir.
Yeah, similarly, if you look into the RMS, which is the second subroutine, again, you did some optimization. Now the runtime has come down from 9.28 to 4.65. But you look into the cost, they are still same. You are still calling 3000 times. Here also you are calling it 3000 times. So this is an iterative algorithm where you are calling the subroutines again and again. So all these subroutines are inside a big for loop actually. Okay, this part is clear to all of you.
Yes, sir.
Yeah, any further questions? Okay, so if there are no further questions, I can go ahead. Okay, so these things I'm not going into the details. These are technical things which you can also understand while doing the labs actually. And then there are other profiles actually. There is the runtime profile of a function, and then how to interpret those numbers actually. So these things will focus in the lab actually. So currently I can skip these things. Okay. So two important things we have understood. One important thing is like, and we should do a overall balance analysis. One is the code balance, which is specific to the code or the application which has been given to us, and the second is machine balance, which is specific to the machine actually, how the machine is going to perform. And both actually are some kind of number which takes into account two information. One is related to the memory, and another is related to the computation. Okay. And then we typically try to correlate these two numbers, code balance and machine balance, to get an understanding, I mean, whether my code is going to do good or bad, depending on how these two numbers are relative to each other. Okay, so the next topic is to really understand and interpret this plot actually, this plot which we have got, this plot. To really understand and interpret this plot, what we need to understand is a couple of these things which are like pipelined functional units, superscalar architecture, data parallelism through SIMD, out of order execution, and larger cache. I think if I start today, that will be okay. Okay.